All right, guys, welcome to day 4 Q&A. So I'm back, Megan Peters, hailing from California here. You all should know who I am by now. And I've got two, hopefully 3 panelists with me today to talk about the tutorial and also to talk about GLMs in general and how you can use them for exciting neuroscience. So I'll let you guys introduce yourselves. So let's start with Jakob. Would you introduce yourself, please, as the celebrity of today?
Okay, so my name is Jakob Macke. I'm a professor for machine learning and science in Tübingen. And in my research, we developed machine learning methods for neural data analysis, which is the topic of today's part of Neuromatch Academy. It's been a great fun and privilege to help organize the day today. I was kind of the day lead for the day that tried to organize things behind the scenes, but primarily that work required me just to find some very good speakers and content makers that did all the hard work on this. So I've been helping a bit, but I've not. The credit for the tutorial should really go to the people that you've seen in the videos. And in the past, I've also helped organize or directed a physical summer school on computation neuroscience. So this has been an adventure to see how many of the good bits of summer schools have been transformed to an online format, but maybe made available to many more people than would ever be able to attend one of those small summer courses that we used to have in the past. So I hope you had fun in the machine learning day. And I'm sure there was a lot of material in it. And I just want to also assure you that the way these summer schools work is that you will see a lot of stuff. And the idea of that is for you to get excited and know what's there. But the idea is not that you have to understand everything right away, or that you have to feel like you have to get to the end of everything. If you try to do that, then there's a good chance you might be frustrated. So just take it as seeing what's there and try to understand as much as you can, but don't feel under pressure that everything has to work right away. All right.
Awesome, thank you. And Sean, will you give us a brief introduction? We should all hopefully know who you are as well, too, from some of the launch parties, but please.
Thanks, Megan. So I'm Sean Escola. I'm an assistant professor at Columbia University at in the Center for Theoretical Neuroscience. I'm also one of the co-founders and board members of Neuromatch, along with Megan and some other folks who you've probably met and will meet. And so I'm really excited. This is actually my first official event in Neuromatch that I'm getting to participate in. I was just telling Jakob and Megan that in my early days as a graduate student, I got to play with some GLM models, looking at some neural data. And I just thought it was so cool that you could model, spikes with if you had the right probability distribution that you were working with, and that you could do inference and learning, and so that's always kind of been something that's continued to make me excited even years later.
Great, thanks. Okay, so before we get into all of the questions, and they're pouring in, so that's great, I'm going to do 2 things. The first is that I'm going to put up a poll, because starting today is where it gets really kind of intense. Yesterday was also starting to get pretty mathy and pretty intense, but we want to encourage people to actually go do yoga as well. So if you click on the polls down below, I want to see if you guys are doing this. You're moving, you're kind of getting out of your chair, because I sit in this chair a lot too. Get out of your chair and move, and go do something fun like that. And so you should see that. Yeah, cool. Maybe tomorrow. Come on, guys, go do yoga. Or do it not with us. That's also fine if you don't want to be in front of a screen as well. But I also want to remind you guys to please go do your reflections as well. This is really important. And so I'm going to put the call to action. There's now a button on the bottom of your screen that says interactive student reflections. If you're an observer, also please type this URL into your browser as well. But especially for the interactive students, we really would like to have you do these. And we're actually going to give you just a couple minutes where we're not going to say anything, and we're going to encourage you, please go do these. And then we'll come back here and we'll talk about GLMs. And so we can just kind of hang out here and chat for a little bit, maybe in the chat. But please go do your reflections. So I have to be quiet now, just for a couple minutes.
You know, Megan, we're at 17-0. I feel like that's not putting in a big turnout for yoga.
But, I know. Well, so maybe you guys do something other than yoga. Maybe we can say if you do something other than yoga, or other. Oh, someone did yoga! Yay! That's great. Right. Wonderful. But if you're not doing the yoga sessions and you're not, doing some of the other virtual kind of fun activities that we're doing here, please also get out of your chair and go do something else that's fun, that is moving around and getting you out into nature or into the air or something like that. Okay. So we'll give you guys just a couple more minutes here before we launch into the big questions here.
So you just hit that link at the bottom to get to the reflections page.
Yeah, to get to the interactive student reflections survey, that should work if I typed it right. That makes it easy for our interactive students. They don't even have to, go into the chat and scroll up to be able to find it towards the beginning. You can just kind of go and do it. And so we can prompt people to do that kind of throughout as well for those folks who are just rolling in now.
And we have some, we probably have some observing students here today. Now, are they doing the reflections as well?
Yeah, they are. They're doing the reflections too, because some of them are following along almost at the same pace or at the same pace as the interactive students. And so we want to hear how that's working too for you guys, your observer students, if you're here, because we want to be able to understand what the difference is between doing this kind of on your own or in a self-organized way and with going through it with a TA and in a pod and doing group projects and everything. So yeah, please do that. Please do these. Okay. So I think that this is probably good for now. We can turn this off, but remember, please hit that button at the bottom of your screen if you are wanting to do this as we go through. So cool, great. So we can actually start to do the questions now. But again, I want to emphasize what Jakob said earlier, which is this is really not meant to be a PhD in a box in 3 weeks. There's a reason it takes 5 years to get a PhD or 6 years to get a PhD, and then you go do a postdoc. And so this is really just meant to be let's have fun and explore. And so we can talk about some of that stuff today too, if you guys have questions about how to kind of engage with the material in a way that doesn't feel overwhelming. So definitely put those in the box if you want to talk about that stuff too. Okay, so we've got some questions already. This is great. So we've got a question about the tutorials. We can see if we can do this one. We don't have the people who actually built the actual tutorial here. What do you think, Jakob? Would you be able to answer the first one?
So you mean the highest voted one?
Yeah. So in the neuron spiking model, I can read it out or you can read it, but I'll read it out for the stream. So in the neuron spiking model, and this question comes from Yi Yan. So in the neuron spiking model example in tutorial 1, was making the firing rate lambda greater than 0 the only reason why we chose an exponential function for the nonlinearity section? Do we have to consider the pattern of our noise, for example, Poisson in this case, as well when making the nonlinearity decision? I guess my question in general is how to select a proper combination of the nonlinearity part and the noise distribution. So I think this is a pretty good question that maybe we can try to answer here.
Yeah, I think this is a fantastic question because it reflects on some of the difficulties that we have when building these models. And there's typically 2 types of considerations that go into building a model and choosing things such as the nonlinearity. And the first one is often computational. So we have to think about what model choices lead to a model that we can fit and handle with that have or that have good computational properties for fitting such a model. And in particular, as you saw in the tutorial, one desirable property of such a model fit is that it leads to an optimization function that's numerically easily solvable, and that's often problems that are convex. So where the fitting problem is convex, as you saw in the tutorials. And for some choices of these link functions, we will get a convex problem, in particular for the exponential function. For other choices, we will not get a convex function. So there's a computational reason for picking the exponential function. In fact, for this Poisson GLM, the exponential function is what's called the canonical choice. So it's the one nonlinearity that leads to a particularly kind of nice form of the formulas. And without going into the mathematical details too much, when we do log probabilities, you often get a lot of logs. And when you choose an exponential function, then the log and the exponential cancel, and all you get back is a very simple formula. So if you use any other nonlinearity, you get a more complex looking formula. And there's only a few nonlinearities that you can take to get a convex fitting function, in particular that exponential function and a soft threshold function, a soft linear function, and there's 2 or 3 other functions that you can choose if you want to have a convex fitting function. So there's some statistical or computational advantages to using the exponential function. But the question that you're asking is also whether, from a neuroscience perspective, whether there's good modeling reasons to pick an exponential function. So do we think that an exponential function is a better model of the underlying biology than a linear function? And one property that the exponential function has is that if you go to higher firing regimes, the exponential function gets steeper, so you're more sensitive to the noise. So the exponential function has this property that in a high firing rate regime, you are more variable, you have more, and you're more sensitive to the inputs. And depending on the system that you're studying, that might be an appropriate assumption. And for some cortical neurons, it is. And in other cases, that might be undesirable. And you might get to a regime where you're too sensitive to your inputs. So to sum up, computationally, the exponential function is very easy and a good choice. Whether it's a good modeling assumption for the problem that you're studying really will depend on the problem that you're studying.
Great, thank you. That was a very comprehensive answer. Yeah, do you want to?
Yeah, I think I'll just add really quickly. I think it's really interesting to think about this problem between computational practicality and the underlying meaning in terms of the neuroscience. And those 2 things often are in conflict. Often they go in parallel, and that's of course the ideal situation. But when they're in conflict, then you have to make some choices. And so, one of the things that I would just want to add a little bit, and you were touching on this, is that although the exponential function is the one that's the canonical one that gives us the easiest form of the equations once you pass it through. There are other choices that still guarantee convexity in your optimization. And so some of those might not be the exact perfect link function and give you the simplest equations, but at least you still have a convex optimization at the end of the day, and maybe there are better choices for the neuroscience. And so that's kind of, there is some room to be flexible while still maintaining computational tractability.
Yeah. So, for example, one function that is a good function that space is if you start off exponential for low inputs, but then become linear for higher inputs, and that's sometimes it's just better behaved than a full exponential, and it's still you still end up with a convex fitting problem.
Great, thanks, guys. That was very comprehensive. Okay, so we can move on to the next question then. So we've got a couple that are tied here. We've got another question from Yian actually about how to interpret temporal filter parameters and whether temporal filter parameters have some sort of structure, does the structure have some sort of biological meaning or implementation where the brain could actually be doing this?
Yeah, I can jump in with the first thought on this. So we know that there are all kinds of time constants in the brain, right? Starting with just the time constants of ion channels opening and closing. And so when we use temporal filters to fit, say, spiking data, we're trying to take into account the fact that there are these time constants. So whether it's from, at the molecular level, whether it's because you have reverberations in a connected network, and so there's hysteresis and there's long correlation times that occur in those networks. So we can try to capture some of those features by using temporal filters when we're building, say, a GLM model of data. One of the fun things, I don't know if you guys touched on this today, but that you can do is you can actually have a model of, say, 2 spike trains, 2 neurons, and you can have a temporal filter for one of those neurons based on the spikes of the other one, and vice versa. And when you do that, then you can allow for the fact that we know that there's these influences, right? So you can think of it as sort of a fake synapse almost, or somehow we can capture these couplings in a real network by using these temporal filters. And so you can think about what are the timescales of those interactions, and we can capture them statistically with these parameters.
That sounds like something maybe you've done in your own work.
So we've at least, the multi-neuron case is not something we actually did in the tutorial, but we talked about it in the lecture. Just to emphasize what Sean said, that these coupling filters, and this is true both for the coupling filters across neurons as well as for these temporal feedback filters, they're often very good ways to get ideas about possible biological mechanisms that might cause these dynamics. But it's also important always to remember that in the end, this is a statistical model fit. So this doesn't unambiguously tell us what the underlying mechanism is. And as Sean said, for example, for these temporal dynamics,
And we're back. We'll just check.
All right.
Are we back, guys? Please say something in the chat if you can hear us, and we will continue on. And we have switched places, which is always what happens. All right. And we're back. Okay. Moving forward. So this does kind of feed nicely into the next question then, which is this idea that you can fit these models, and they're statistical models, and they do a great job of maybe explaining or predicting what's going to happen. But then the next question is, okay, well, what is actually the brain doing? Is this actually what the brain is actually implementing? And so the next question is, can you talk more about the GLM assumptions? Do the regressors, the independent variables, or the X matrix need to be independent from each other? What would be the best way to quantify? Oh, actually, there was one. Sorry, I'm gonna switch because I started reading and I realized I was gonna go to the other question first. So just kidding. Let's go to Yiming's question, which is about the brain. So this is today we've learned GLM and its application in encoding and decoding. Problems. I'd like to know whether our neurons act in the same way. Is there any evidence that neurons are encoding or decoding information in some ways which is equivalent or similar to the GLM? So what do we think about this question? Is this actually what the brain is doing? It's a philosophical question.
I mean, I think Jakob's he touched on this in his response to the last question, which is that this is a statistical model, right?
Yep.
This is not ground truth. What we're doing with these models is trying to capture as much of the statistical structure in the data as the flexibility of our model will allow. And only after we've done that can we try to make some claims about what it says about the brain that ultimately had originally produced the data.
Yeah, I like that.
So you look at your parameters and then you try to make an interpretation.
Cool. So we have a third panelist now with us. This is Rishi. I will allow you to introduce yourself, please, and let us know where you're coming from and how you want to contribute to this conversation.
Hi, everyone. I'm Rishi. Sorry, for some reason, I got a Thursday invitation because I'm in California and it's the middle of the night. And so I was expecting this to be tomorrow, which is why I look a little bit all over the place. But
it's okay.
I'm a professor at UC Davis, so I'm new here about a year in. I'm split between math and neuroscience. And I do some work in theory, trying to build theories of distributed neural network. And then I do some more data analysis work. And I've been doing stuff looking for low-dimensional manifolds in neural data. And yes, I'm excited to sort of take your questions.
Great. Okay. Thanks. So, can we do this next one? So, can you talk more about GLM assumptions? Do the regressors, independent variables, or X need to be independent from each other? What would be the best way to quantify the relationship between independent variables and then feed it to the GLM? What do we think about this one?
Okay, I can take this. So, so one thing that we do not need in a GLM, so we do not need the covariates or the inputs to be independent. I mean, this is in fact one of the cool things about GLMs, that you can use it to characterize the neuron's response to different things that might be correlated with each other, okay? So they do not have to be independent. Having said that, if they're completely correlated, so that you'd have two inputs and they always come up together, then it will be very hard for the GLM to figure out whether the first input or the second input is the one that's a better predictor of spiking, because they always come up together. So they don't have to be independent, but if they're too correlated, then the fitting problem you can get can make it very hard to figure out which one of those two is statistically the best explanation. Yeah, so in that sense, they do not have to be independent.
Okay, great. All right, so let's go ahead and start with the next question then. So here's the next question. What are the advantages and disadvantages of L1 and L2 regularization, respectively? I used elastic net regression to perform regression, resulting in all theta values equal to 0. Did it mean that the dependent variable doesn't have any significant correlation with any predictors? If there are ways for me to improve the model, or is it definitive results?
I could say a little bit about L1 versus L2. I think, it's kind of, when you're regularizing something, you're trying to exclude certain kinds of structures. You're saying that, maybe I don't want some really big positive parameters and some really big negative parameters. that cancel out to fit something small. And so you're kind of working off this intuition that whatever model you're fitting, in some sense, the coefficients are meaningful in some way. Meaningful could mean either that they don't take huge values or that they're sparse, and so on. And so whenever you're thinking about regularization, I think it really helps to kind of sit down and ask yourself, what do I expect from my model? What are the natural physical constraints? L2 regularization is a very natural thing to do. It really penalizes big things. The other reason to really like L2 regularization, L2 structures are mathematically very well behaved. And so there are lots of efficient algorithms for them. People mostly use L1 regularization as a proxy for sparsity. And so by sparsity, I mean that a lot of your coefficients are 0. Now, it turns out that actually finding a sparse solution is a really, really hard problem. It's, NP hard. But L1 regularization is a good approximation to sparsity. And so whenever you think that your problem should have sparse structure, L1 regularization is a good proxy to use them. Elastic nets use both, and you have some flexibility to play around with how much you weight one versus how much you weight the other.
Great,
yeah,
thanks.
Thanks. Maybe just to add to the second part of the question, if you do an elastic net and all filters come out 0, there's 2 possible reasons for that. Either your regularization parameter is too strong, and the other potential reason is that maybe your inputs actually are not predictive. Maybe having everything 0 is the best possible prediction because your inputs are not predictive. Either of those 2 scenarios is likely going to be true in your situation.
Okay, great, thanks. Okay, all right, so let's go ahead and do another one. Okay, so according to the tutorial, so this is now about the tutorial, so Jakob maybe we'll be able to do that for you. Using GLM, when most features don't affect the outcome, we can assume that the parameter vector is sparse, but it doesn't mean that non-zero coefficients indicates that only those features carry useful information. So when can we assume that some input features really are not important? I guess the way that I would assume this is that, or the way that I would start answering this one would be that it kind of depends on the definition of information that you're trying to model here. If the information is really just contained or specific to the one particular outcome variable that you care about, then you can say that these neurons do not maybe carry, or these units do not maybe carry like particular information about that particular thing. But that doesn't mean that those neurons or units or voxels or whatever are not actually doing anything. And so it means that maybe you just need to change your question a little bit. I know this is kind of a broad, high-level explanation or answer to the question, but maybe that'll get us started in answering this particular question.
Yeah. So yeah, I'm not 100% sure whether I'm answering the question correctly, but it also part of the question seems to be that let's say you have 2 parameters that are non-zero, and does this mean that both of these inputs, let's say both of these upstream neurons, are both synaptically connected to the neuron trying to predict? So does a non-zero parameter actually imply a causal influence of those inputs onto the neural firing? And even when the coefficients are non-zero, so even when they help predicting, it might be that the underlying causal structure is not aligned with that. So it could be that you have 2 inputs, and the first one is really truly predictive and causally causing the neuron to spike, and the second one is just strongly correlated with it. And then it can be hard for the GLM to figure out which one it should use, and it does non-zero parameters to both of them, although really the first one is the one that carries the prediction performance, and the other one is just tagging along with it. In the infinite data regime, if this is a perfectly observed model, then one of them should go to 0, but for finite data, even when everything is observed, they might get non-zero values. So there's always this extra level of caution that we have to apply to interpreting parameters, both for the ones that are non-zero and for the ones that are non-zero. And we always have to remember we have finite data, we have an imperfect model, and we have also underlying structure that we're not observing directly.
I just want to emphasize one thing you said. So the point of using an L1 prior to try to force parameters to zero is exactly to deal with this problem, right? As you said, if you had an infinite amount of data, you should be able to figure out which one is the causal one and which one is just the correlate. But unfortunately, that's not what the real world gives us, and so we are left with the ambiguity. But that's actually the goal of using L1 regularization.
Yeah.
All right. Cool. Thanks. So let's keep going. We're just whipping through these. I like this. Okay, so let's do the top rated one then, if that's okay. Another question from Yan. In the outro, you said that the GLM is good because it gives a unique solution and we can obtain it very quickly. However, as to L1 regularization, we don't have a closed form solution. It means it's not unique and quick anymore. Does this mean that L1 is not a good norm or a good way to do it for GLM? Good, not suitable for GLM. I don't know that I can answer the question.
I can jump in. It's not the case. Just because you don't have a closed form solution doesn't mean that the solution is not unique, right? With an L1 regularization, you can still have a convex optimization problem with a single solution. It's just, it has increased computational burden compared to the simple, more mathematically well-behaved L2 case. So it's important that we don't conflate these two ideas. The L1 is totally suitable for the GLM if the goal is to try to figure out which of your inputs are the ones that actually are affecting the output, right? If you want to impose sparsity. So yeah, I think I hope that I got that right, but I think that's the important point here.
And when we say easy, we don't mean necessarily there's a closed solution. We just mean there's a good algorithm for finding the solution. And convex fitting problems from an optimization perspective are easy, although that doesn't correspond to the notion of easy we have as undergraduates working out things analytically. In fact, convex optimization problems are often easier to solve than complicated analytical forms when it comes to evaluating them computationally.
That's an interesting idea. So just because we can write a nice expression in our homework assignment or in our paper, that doesn't necessarily mean that that's better than using some algorithm to get the answer.
Depends on what your goal is, right? If your goal, because we started the whole school with goals of the models. And if your goal is to get to an answer that gives you good predictive power and that fits behavior or that fits the system that you're looking at, then this is potentially a great way to do it, even if you don't have an elegant, beautiful closed form solution. If what you care about is beauty and closed form solutions and simplicity in that respect, then this maybe isn't the right way to go about it. And so again, it's all about like what you care about, what you're trying to use the model to get at.
I'm sure there are good examples where you can get a closed form solution and you use that for analytical insight to understand the system. But actually, when you do the computation, you would do it in a different way. I can't think of one off the top of my head, but I'm sure there are many examples like that.
So some eigenvalue problems fall into that, where if you can very quickly find the eigenvalues computationally, and like the expression that would go along with it is actually numerically not something you want to implement. Yeah.
Sure, that makes sense.
All right. So I think I'm going to skip around here because the upvotes are not making them in order for me. So I'm going to go to a question from Rebecca, which is, I want to know more about why we have a nonlinear part in the GLM. What's the point? Why do we do the nonlinearity? Plus, I believe there must be combinations between the nonlinear and the linear and nonlinear parts. So how do we choose? And I assume that what you mean, Rebecca, between how do we choose is how do we choose which ones to put together, and how do we choose whether to use a nonlinearity at all? So this is actually a really good question. So again, I'm going to let you guys take it away. But this is the type of question that we like here at Neuromatch Academy, because it's about not just you have this fancy tool and you plug it in and it gives you an answer and then you publish a paper. It's about which is the best tool for the job and how do you select that one, and what are the things to consider as you're selecting your tool. So good question. Great question. So how do we choose?
So I can give you some thoughts. So like I think it's kind of interesting to think about what kinds of structures a linear model can capture and what structures it can't. And it turns out that there are a large number of pretty natural structures that you actually do terribly wrong if you try and fit in a linear model. And so, I think tomorrow you'll probably talk about PCA and dimensionality reduction. And it turns out that anytime you have sparse structure in your data, a linear model will just do terribly. It'll really, really overestimate the structure in your data. It'll tell you that there's much more, there's much more variability than there actually is. And so then you say, okay, well, what nonlinearity do I need? And there's sort of two ways to answer that question. One way to answer that question is kind of mechanistic. You say, let me take what I know about my system. I know that neurons get some input that comes in, they integrate this information, maybe it hits a threshold and then it spikes. And so can I build a linear nonlinear model that captures that, use linearity as much as possible, but put the nonlinear parts in where I think they're important. And for neurons, that's the threshold. So you want to capture something like that transition from rates to spikes. A second way you might try and combine linearity and nonlinearity is more mathematical or statistical. You might say, what kinds of models can I do good inference on? What kinds of models can I solve easily? And so GLMs, for example, pull from this set of ideas and statistics about exponential family models. And those models combine linear and nonlinear structure in a particular way that both gives you a lot of flexibility and allows for easy inference. And so, we like linear. We want to use linear as much as possible because it's easy. But sometimes we need nonlinear. Where do you put the nonlinear? One set of intuitions or insights comes from these mechanistic models. What do you know about your system? If you're good Bayesians, you try and use what you know about your system. And another set of insights comes about because, you're lazy, you want to be able to find a model that you can actually solve and get on with your life. And so some of it comes from mathematical tractability. But, I think it's an interesting and deep question.
I think there's a related point is it also comes from the data, right? So depending on the kind of data that you collect, then that sort of puts you in different categories of the kinds of models that you might want to use. Now, of course, you can force data into kind of any bucket you want to force it into. So for example, if you have spikes, you might think it's natural to use a nonlinear model that has positive rates, right? So something like a Poisson GLM. But you could, of course, bin your spikes and count them up and get a number and then use a linear model. And so there's another question, which is how much do you want to take the data in its natural state and try to build a model to match that versus try to massage it into a way that fits into some other simpler system that you might feel more comfortable using those tools.
Yeah. Yeah. So, I mean, both this question and the one we had kind of quite early on in the Q&A, they come back to these general issues on how do you build models, right? And this is something that that other parts of neuromatch are also dealing with. What we told you about is about some mathematical tools you can use to predict spiking or decisions, but much of the work is actually selecting from this toolkit of many possible models you could build, the model you actually want to build. And there's often an iterative process where you start off with a model that you think this is some good compromise between tractability and what I think is right about the system. Then you apply this to data and you figure out something goes wrong or seems unplausible, and then you refine your model. but there's a lot of hard work and thought going into building a model that's both appropriate for the question at hand and that's also tractable computationally. And this is much of the hard work that on an example where you don't know what the right answer is, can take a lot of time to figure out what is the right the model to build. And that's the art and science in statistical model building that is still left for you to do on your data.
Definitely. These are great questions, guys. Keep them coming. Okay, so let's see. We've got one at the top here from Cecilia, which is when different stimulus sources are presented simultaneously, is it possible to use a GLM to get temporal filters in other fields, which is called transformation, I guess, to those different sources from the same recorded signals, one recorded signal, but over two stimuli? Let me see if I can parse this. Let me think about this for a second. Temporal filters with other fields, which is called transformation, I guess. Okay.
So, I mean, I'm not sure whether I'm answering the question correctly, but some of that seems to be, can you use these temporal filters also in scenarios where you have multiple inputs presented simultaneously? And the answer is yes. So you can take as your input, let's say you have two stimuli, and then you can say my inputs are the stimuli now, the stimuli on the previous frame, and the stimuli on 2 or 3 frames ago, right? You can just say, I make myself a transformed, expanded stimulus that consists of just stacking together the stimuli I had in the recent past and using that as one bigger set of regressors. And so whenever things are observed, you can stack them together into stimulus, into covariates. You can also nonlinear transform them. So you can say, I take the stimulus and the square stimulus and the cubic of the stimulus, and I make myself kind of a big covariate input and just throw my GLM on it. So you can always do this. At some point, you might obviously run into computation problems or into overfitting problems, but conceptually, you can always transform your inputs in such a way to kind of build a more powerful predictor.
Great, thanks. Anybody have anything they want to add to that?
Well, there's this comment that Young Cheng asked, which is like in the cocktail party problem. And I think that the way to think about this here is, let's say you have just one covariate, call it X, but you also have reason to think that X is at every time point is, you only measure X, but at every time point you think it's a sum of, S1 and S2. And can you figure out what those different components are? And there are ways to do that. It's not, you would have to add additional machinery on top of the GLM, some sort of source separation, maybe a matrix factorization kind of problem on the data. So I think that that's an additional complexity that you'd have to build into your model to try to get to that sort of solution. But it is possible in this framework.
Great. Okay. Thanks. So we've got time for a few more here. Keep them coming, guys. But we can also take questions that are bigger and broader, that are, these are very nitty-gritty, like kind of detailed questions, which is fantastic. And I'm so glad that you guys are asking these. But we can also think about how to fit GLMs into a kind of a broader framework as well. So don't be afraid to ask kind of broad questions as well as detailed ones. Okay, well, here's actually a broader kind of detailed one, a broader one that kind of applies outside of GLM. So this is great. So Rebecca is asking, sometimes, especially with behavioral paradigms, we cannot get enough data for both test and validation. How do we balance the validation data and the test data? So this is a much bigger question than just GLMs, but this is great. So let's talk about this one. And so Hanbo is given a comment here that says, leave one out is an effective way with a small data set. So this is about, are you splitting your data into training and test, or do you have training and cross-validation and then a test set, or those kinds of questions? So we can talk about this a little bit maybe, which is good because this applies not just to GLM day, but to kind of any model fitting. So I'm glad that we're talking about this. So if any of you guys want to jump in on this one, I'm happy to let you take the reins here.
Yeah, I mean, I can provide an answer. I wish there was a better answer than the one I'm going to give you, but it's very hard to come up with a principled way to choose the balance between your training, test, and validation set. One thing that's often done is that typically you have like something like 80% of your data in the training set, 10% and 10% each in the test and validation set. So like a split where most of your data is in the training set. For most models, you will need that. And this often is a challenge, as you say, in particular when you have small data sets. One thing that's really important, though, and I want to emphasize, is one thing you should not be doing is to play around too much with that split. You can't try out all possible ways to split it like 80%, 90%, 95%, leave one out. If you try out many of those splits, then what's really happening is that the choice of how you split this is becoming like a hidden fudge parameter of your model or of your analysis, and you do this too much. You allow yourself to have extra flexibility, and that might give you optimistic estimates on how well this regression is going. So whatever split you should do, I mean, pick a reasonable split and then stick with it and don't play around with it too much. Otherwise, you might be fooling yourself into thinking that you can predict better than you actually can.
And if you do that too much, then the next time you do it to a different data set with the thing that you optimized for this data set, you're going to have the same problem over again. And so it just kind of takes the problem to the next data set instead of staying within your own, the current data set.
Yeah, there's this idea, it's called the garden of forking paths in analysis, that the more free choices you can make, the more hidden control you have over what you come out. And that's always a dangerous garden to go into when you want to have reliable results.
Actually, I'm curious. This is not something that I'm an expert in at all. I'm curious, when you have, say, simpler models, like something that you can that's convex, so you feel like you have computational tractability. Does it make sense to do something like leave one out and just try all possible, train all possible training sets and see if you can get better insight by doing that rather than just doing a single split?
There's a long answer, which I'm not sure we should discuss here, but there's a trade-off also when you do leave one out optimization. Then you have a gigantic overlap in your test sets, which affects the independence of the estimates you get. So doing leave one out is not necessarily kind of much better than taking a bigger data set, having a bigger training set.
So the short answer is you have to try some things, but don't try too many things. Right? Come up with a principled reason why you're making the split the way you are based on the size of the data set that you have. Unsatisfying answer, perhaps, but what we're trying to do here is build a little bit of intuition about what the options are, so and how to do that in different types of data sets. Okay. So we've got just a couple more minutes here, and we've got a few more questions that are all kind of tied with a few right up at the top. So maybe we can do these right up at the top. Rebecca is asking, under what kind of circumstances can we use the GLM model? To be specific, what should we need to consider when choosing the GLM model apart from the features of the input and the output variables, that is the underlying pattern? I think maybe this is like in respect to choosing a different kind of model that you might use that's not a GLM, maybe like some other kind of deep learning model, perhaps. I'm not sure exactly. So Rebecca, I'm going to take a best guess here at what you mean. But maybe if there are other models that you could have chosen, how do you select that the GLM is the best one? I think the answer for me would come down to the goals also first. So I know I'm leaning heavily on that, but that's kind of the big picture that we want to put everything in is, what are you trying to explain? What level of explanation are you trying to get at? And also, what data do you have? So you've got, the features of the input and output variables, but given that GLM can be used for both encoding and decoding models, but you have a lot of other choices also for how you can have explanation build up to connect all of the variables in your system. It's really just about what you're trying to do with it. I know that's also one of those unsatisfying answers. It's like, it really depends, but it really does, unfortunately.
Yeah, maybe just to add to this, and GLMs or linear models are very simple. So when you don't know what to do, a GLM is always a good model to start with, although depending on the goals and the data, you might end up using a more complicated model later. But you should always try out the simplest reasonable model before you jump to something more complicated. You want to learn much more complicated techniques later in the summer school. So GLM relative to those is actually a very simple thing to try out. So if you're not sure yet, this is a good thing to start with.
And it comes nicely in some packages as well, right? So you don't have to build it from scratch. It is a nice thing to start with to try to understand even something as simple as, do I have enough data to be able to build a model to begin with? Do I have enough data to be able to pull the signal from the noise? This is often a great way to start, to say, I've got these data. I'm going to type into, scikit-learn. I'm going to use this logistic regression model. I'm going to use this kind of standard approach because it's easy. You don't have to build it from scratch like you did in the tutorials today. You can use the packages that are built into your favorite, software package, and you can try it out. So it's a good way to start.
And they're good building blocks.
The easy models are also easy to program, so you don't get as much benefit from using the packages.
That's true. And by learning how to build it from scratch today, you understand it a lot better than just typing like model.train. Like that's all you get, right? You need to understand really what it's doing underneath. Rishi, sorry, you were saying something?
I was just going to say that they're also nice building blocks. Like you can think about a deep network as a bunch of GLMs sitting on top of each other. And so if you understand what a GLM's doing, then you can say, well, what are 2 GLMs doing and what are 10 GLMs doing? And you kind of build up intuition that way.
All right, great. So let's maybe do one last one here from me, Anne, which is, why is a linear model more interpretable? And so the simple answer here would be, our puny human brains have trouble processing and running models that are nonlinear in our heads. That's the simple answer, is that it's hard for us to think about these. So if you do care about interpretation, you have to look at the limits of human interpretation capacity. I don't know if anybody has a better thing to answer in this way.
Another thing to notice is that a linear model basically does the same thing at every point in your stimulus space. A nonlinear model, nonlinearity basically says that what you're doing changes depending on where you are. So if you think about the way x goes, the line, it looks the same everywhere. If you look at x squared or x cubed, or something more complicated, it starts to get sharper as it goes on. With the linear model, you can just tell a simple story that applies everywhere. Take this input, multiply it by 3, take that input, multiply it by 5. For a nonlinear model, you might say, oh, if this input is small, we're multiplying it by 3, but if it's big, we're multiplying it by 10. But then what about if this other input is small? Things can combine in more complicated ways. A linear model is multiplying.
That's interesting. We were talking about this, I think maybe before you joined, Rishi, about that in some cases you might not want to use the canonical link function because it's better for your understanding and interpretability. So, for example, Jakob mentioned that you might want to use a function that's exponential when it's small and then linear when it's larger, and that also has this nice property that in that larger regime we know that for all points of x it's doing the same thing, and so that's sort of that additional interpretability. So it has these kinds of additional convenience.
Cool. All right. Well, guys, it is 12:01. So I think that is probably a good place for us to stop. We've got some other questions, though, that we did not get to. So as always, please take these to the discussion forums. This is a great way to continue the conversation. and to get some of these detailed questions answered. And also, just because we didn't get to it today doesn't mean it's not an important question or a good question. And so please do take them to the discussion forums and keep the conversation going there. So thanks very much to our panelists for joining me this evening. And I hope you guys have a good rest of your night. Okay. Thanks, guys.
Thanks, Megan.
Bye.
Thanks.
Thanks, everyone.
Bye.
Hello, everyone. Welcome back to the Q&A sessions today for GLMs. And it's my pleasure to have a nice panel here that is composed by Christina Savin. Christina is a professor of neuroscience and data science at NYU. And then we have Anqi Wu, who is a postdoctoral fellow at the Center for Theoretical Neuroscience at the Zuckerman Mind, Brain, and Behavior Institute, Columbia University. And we have Memming Park, who is in the Department of Neurobiology and Behavior at Stony Brook. So maybe now in reverse order, Memming, would you like to briefly introduce yourself and maybe tell us something about why GLMs are the most important thing in your life? Or maybe not.
I would say cats are more important than GLMs. Thank you for the introduction. Yes, I can tell you how GLMs are important, but first, brief introduction of myself. I'm Memming. I'm very interested in understanding how neural computation is implemented in the brain, and in particular by analyzing neural data coming from different experimental setups. I'm computational, so I don't do experiments myself. And GLM is very important in my life in many ways. Most recently, I used it yesterday. Yesterday, I was trying to figure out the intrinsic structure of sequential or temporal structure in music. And I was telling my student to analyze data using basic GLMs to fit a autoregressive model to predict the next note in the music from the previous notes. So this was not a neuroscience problem, but oftentimes what you can use these models for is you can first fit the model for the task, and then you can try to open that box to see if the principle that your statistical models are using are similar to what the neural computation would be. It would provide you with hypotheses. So that's where I used it most recently. I use it pretty often, but it's not my main tool. I really like it as a baseline. It gives a very good performance across many different problems. But on top of it, I always try to add on top of it, extra, more powerful tools to understand the brain.
Great, thank you so much. Christina, would you like to introduce yourself briefly and say a few words about GLMs and how they're important for you?
Yes, so I'm Cristina Savin. I'm a assistant professor at NYU. I'm both affiliated with the Department for Neuroscience and the Department for Data Science. What we do really is sort of trying to understand how computation happens at the level of neural circuits, primarily using theory, but more recently we've increasingly focused on the new development of statistical tools for the data analysis part of the question as well. So historically, we haven't used GLMs all that much, but we spent a lot of time using GLMs recently in the context of a new project that we have, where we're trying to understand how neurons in different areas of the brain respond to a monkey, in this case, so animals doing complex naturalistic tasks. So we have a monkey in virtual reality doing the spatial navigation task. So the monkey sees a flashlight that tells it that is going to be reward over there, and it navigates using the joystick and tries to get to the reward. And as the animal is doing this, we're recording activity for a whole bunch of different brain regions. And these are brain regions where we don't really know what the neurons really care about. So we're using GLMs, more generalizations of GLMs, as a first pass to the data to figure out what it is that these neurons actually care about from this many potential task-relevant variables.
Awesome, thank you so much. Anqi. Would you like to do a brief introduction of yourself and tell us something about the GLMs for you? Your video is a bit frozen, but I think your voice is coming through.
Oh, can you hear me?
Yes.
Am I moving? Okay, great. So hello everyone. I'm Anqi Wu. I didn't join this session yesterday, so people might not see me yesterday. So I'm a postdoc researcher at Columbia Zuckerman Institute. My main research is developing machine learning methods to understand the neural data, understand the brain, and also understand animal or human behaviors. So GLM to me is like, as I think, so model fitting first is a very central part of the research I've been working on, but many things, real world things, or like the brain, the neural activity, the relationship we want to study is highly nonlinear. Therefore, GLM is very critical. Usually when people talk about model fitting in neuroscience, people talk about GLM because things are highly nonlinear in real world scenario. And as I show in the slides in the tutorial, I'm not only interested in understand the encoding, like how to map the stimulus to neural activity, but as well as from the neural activity to the behavior. And also, GLM is way more powerful than you think to model many more different problems in neuroscience. So it will be interesting for you guys alone to explore yourself. But I just want to say, like, GLM is really important to study neuroscience problems. So
Great. Thank you so much. Oh, you just unfroze. That's awesome. But we heard you. We heard you perfectly. It was just you had a still image for a second. But that's perfect. That's fine. Like, as long as we hear you, that's the most important thing. Okay, so I suggest we start answering some questions. So the first question is by Amiretsa Farbaksh. And I'm sorry if I butcher your names. This is very hard. Okay, so Amiretsa's question is, when using GLMs, we typically use gradient descent for optimization, but it's said to be biologically implausible. Why? Also, I have seen Conrad talking about the brain using backpropagation. What algorithm does the brain use during backprop for optimizing parameters at each stage, if not gradient descent? Who would like to give that a shot?
There's some tricky bits there, right? So, I mean, backprop is a form of gradient descent, right? So those are not separate things. So that's an important point to articulate. Whether or not the brain does gradient descent and on which objective, that's a much more expanded question. So there are people who do research on how the brain could approximate something like backprop using local operations. So the reason why you would think that it's not possible for the brain to do something like that is because the computations that you need to do require information that's distributed at the level of a whole bunch of neurons, and neuron A doesn't know what the information that neuron B has, and the other way around. We are working on approximations of backprop that doesn't have this property, where the information is local enough that you can actually use it as a learning signal for each of the neurons. But it's definitely not a solved problem. So this is a current area of research.
Yeah.
I think we will have more discussions in week 3, where we learn about the real neurons' behavior and learning paradigms over there. I just wanted to add on top of this. So the first part of the question was about GLMs and why is GLM learned through gradient descent or other optimization techniques. I mean, one thing to keep in mind is that GLM is not a model of the biological neuron. I think day 3 and today's discussions in the lectures and the tutorials probably made it clear that these are statistical models that capture some relations, but they're not necessarily a proper neuron model, right? And the way that we're fitting them is by fitting the input-output data patterns, not by we're not trying to mimic how the brain is learning in this case. So for us, the best thing to do is to find the best statistical model to capture what's in the data. And that's why the question of is this biologically plausible or not does not matter in our case. But of course, if we were fitting a model of how the brain works in terms of its mechanistic level, then we probably should not or rely less on these principles.
I mean, people have used GLMs as a more mechanistic model. For example, in the early work of Jonathan Pillow in the retina, I think that they're sort of like the map between what we use as a statistical characterization of neurons and what the neurons actually do is a little bit tighter. It's still pretty loose, but I think at that point people actually intermingle them a little bit, and maybe that's a point where it makes sense to ask the question. But in general, when we do data analysis, we try to understand the structure of the data and use that structure in a theoretical context to understand how the neurons do the computation. We're sort of like, we're not in one step trying to understand how the neurons do the same computation.
Great. Thank you so much for those answers. Okay, the next question is by Abin Krishnan. Abin asked, has the physicist/engineering approach to neuroscience really helped in solving brain disorders? Why is that? So why is it that the neurologists rarely give an ear to computational neurosciences? Or is it that computational neuroscience is more of theory and less of practical application? That's an interesting
Memming, this is on you.
Well, unless Anqi wants to take it. Okay.
I'm just currently offline again.
Oh, really?
Oh no, you're just not. There's no video.
I'm still frozen.
Yeah, it's not off.
Yeah. So,
but don't worry about it. We can hear you perfectly, so that's fine.
So computational neuroscience is a big field. I would say there are many different aspects of computational neuroscience. There are more theoretical parts. There are more, more computational modeling parts. Trying to understand the principles of computation in the brain. There are also more engineering type, right, analysis, trying to help different kinds of patients and have more applications. So there are certainly parts of computational neuroscience that are relevant for clinical applications. I would say, I would give you an example of where I'm coming from. So I am working on one of the projects that I'm working on, and I'm very excited about, is trying to help comatose patients. So as you will learn in a few days, I think in week 2 or 3, there will be dynamic systems lectures. And what I'm trying to use these computational neuroscience models for is to try to help them wake up from certain types of unconsciousness. So trying to perturb their brain and try to understand how electrical stimulations or other kinds of stimulations would perturb their brain and how to get them out of that unconscious or tractor state. So there are certainly people who are working on these problems, and there are many different interfaces between computational neuroscience and more engineering or more clinical applications. So I would say that they're tightly linked in many places. But there are, of course, a lot of people who are just working on theory.
Yeah, I mean, basic research is going to eventually matter for things, but it's not an immediate link to a clinical application most times. I think brain-machine interfaces are the most obvious point of intersection, where the GLMs are sort of like almost used the same way we're using it in the basic research, but with an application in mind.
I believe they heard from Byron Yu yesterday.
Anqi, do you want to add something?
No.
just making sure here. Perfect. Thank you so much. Next question is by Ken. When fitting linear Gaussian regression models, why can we augment the... I should click this before I read. Okay, so why can we augment the design matrix to account for the mean of y by adding a constant 1 to the matrix? Who would like to take that?
Anqi?
Sure. I mean, you can do that. I think there are just multiple ways of doing it. You can either pre-processing that by demean the data, or you add a constant 1 and learn the offset to account for the mean in the data. Actually, I would suggest maybe doing the later in many cases. Well, I don't know. People do both. So it's actually, I actually don't, maybe there's no strong like preference to which one. To me, I did both. I sometimes demean the data, sometimes I add a constant if I'm too lazy to do that. So I don't know. Other people have opinion about this.
I mean, one thing to note is that for maximum likelihood, these are equivalent procedures.
Well, if you have a Gaussian observation model, if you have a Poisson model, you can't demean. So you have to do
within the context of linear Gaussian models, yeah, for maximum likelihood, adding a bias term, having a 1 in the matrix, or demeaning the pre-processing data are all equivalent. They will give you the same result.
Yeah, but Christina has made a really good point. For Poisson model, people prefer to add a constant to learn the offset instead of demean, right? If you demean the data, you get negative values, which doesn't make sense for Poisson model. So yeah.
Yeah, so putting the bias in the parameters is more natural for the general setting.
I agree.
Awesome. Thank you. Okay, the next question is by Matteo Mancini. Matteo asks, how does a linear Gaussian GLM correct for correlation between regressors, and how the covariance term is simplified in the spike-triggered average scenario? So how is it simplified?
Do you want to take this, Anqi?
How does a linear Gaussian GLM correct for correlation? I don't actually quite understand this question. So in the model we have, we actually assume, oh, okay, sorry. An example we gave in the tutorial, we assume independence among regressors, which means we could write the log likelihood as a sum over sorry, I confused that point. So we okay, sorry. So for the linear case, we don't. Okay, I think this is true when we talk about multiple linear Gaussian model, and okay, so I am confused with the correct term. So usually when people deal with multiple linear Gaussian model, people assume Gaussian distributions, and if you have correlation among regressors, you just assume multivariate Gaussian without independence among regressors, right? If you assume independence among regressors, then okay.
Maybe I can take.
Yeah, I confused myself again with the Gaussian noise thing. Sorry.
So for spike triggered average, I think there are two different formulations. You can just weight the stimulus by the spike count, or you can also correct it, have an additional term of correction of the correlation within the stimulus distribution. Both of them are consistent estimators for the receptive field, meaning if you have infinite data and if you fit perfectly, then they will both converge to those correct solutions. The one that has that correction for the correlations, the XX transpose inverse part, that would converge faster. It's more efficient in a sense. But they're both correct formulations. I don't know if that answered the question.
Yeah, I think that there's a follow-up in the chat. Yeah, so the XX transpose inverse thing is the correction.
Yes, that's the correction, and yeah, that will give you a more efficient estimator, yeah, for smaller data. But for infinite data, they do converge. I think the result is well described in Paninsky 2003, the covariance properties of the 3 spike-triggered analysis paper.
Yeah.
Awesome. Thank you so much. Next, we have a question by Amit. That's about L1 versus L2 regularization. When should we use each? Can you give realistic examples of neural data that require one method over the other?
It's tricky, right? Because these are sort of specifying assumptions that we have a priori that come from neuroscience knowledge, in a sense, more than anything statistical. There's also sort of like when we don't really have any particularly informative knowledge, for example, in the context of this kind of experiment that I was mentioning at the very beginning, where we just try stuff and do model comparison because we have no idea. Yeah, there are things to try. It's not always perfectly clear what's the correct answer. There's also the combination of the two. So you can do something like an elastic net when you combine the L1 and L2 and let them fight each other out and not worry about it at all. So there are different kinds of solutions.
It's a sort of an art, I would say. with experience, you'll know better. And sometimes you're not satisfied with either, and you'll look for better priors, which I think is coming soon in your Bayesian lecture.
Yeah.
Yeah, I think L2 norm is more conservative. People might turn to choose to use L2 norm at the beginning at least, and you see how the performance is. And unless you have very strong prior knowledge about your model, then you can, like, which means you assume the relation, like the mapping would be sparse, and then you use L1 norm. For example, if you try to decode the relationship between some neuron and some output behavior, and like not all the neurons respond to, not all the neurons fire during this behavior, then you can impose some sparse prior or sparsity over the relationship. Then most of the neurons will not be firing when you learn mapping from the neural activity to the behavior. And this is very common for people who are more from cognitive side. And if you do a lot of fMRI experiments, and this is usually true, because in fMRI, if you try to do decoding from the whole brain fMRI and fMRI data to human behavior, then usually you will use L1 norm to do the decoding task, because not all the neuron respond to the specific behavior. So
yeah. So there's a follow-up in the chat that I think it's important to mention. So if you have like a lot of regressors, another reason why you might want to use an L1 is for interpretability, that you want to sort of attribute blame to a small set of possible causes to the neural responses of this thing, which is the case again in the Macke virtual reality spatial navigation experiment, where we want to sort of isolate relatively small subsets of features that these neurons care about. Where it's not necessarily that we assume that that's the case, but we kind of enforce it a little bit in the model to get a more interpretable result. Yeah.
Awesome. Thank you very much. Okay, the next question is by Anna Lebedeva. Can we compare models using likelihood when models belong to different classes? If not, how would we compare performance in this case? For example, RL versus GLM.
We can, for reasons that will become apparent when you actually learn about probabilities properly. So basically, all of these coefficients, all these sort of goodness measures that we're getting from the log likelihood and regularized log likelihood and stuff like that, they're actually under the hood probability, so they're in the same units. So that means that you can compare them across models if done properly. But it's really hard to explain this without talking about probabilities, which I don't know how to do without you teleporting yourself into time to next week or whenever it is that you're learning about these things.
Well, you can give it a try with sort of basic concepts, I guess. I mean, they know about probabilities. They don't know about the Bayesian formulas.
Yes. But, so all of these things tell you what's the probability of your data under your model, right? So they're the same kind of quantities. And the probability might be have the form of a Gaussian or might have a different kind of form, but they're still probabilities. So as long as they're normalized, then you can do the comparison. Memming, you look confused.
I am slightly confused. I tend to avoid comparing these raw likelihoods.
Yeah, this is why I said that they need to be normalized for them to actually be probabilities and for the units to be the same.
Right. Even with the proper normalization. Oftentimes I don't think they're on the same stick, right? If you have Gaussian likelihood versus Poisson likelihood to capture binary data, I tend to avoid comparing them in terms of the probability. One
I believe in model comparison, Bayesian model comparison rules.
Bayesian model comparison, I totally agree.
Yeah.
But if it's just a likelihood.
Yeah, well,
especially when it's just a likelihood on the training data set. One thing to be careful, of course, when you're doing model comparison, I think this was not the question, but just a side note, is that if you try to compare these likelihoods across vastly different models, what could happen is that you might have more parameters, more flexibility, or some other kind of differences in the fundamental model, like Gaussian and Poisson, that would make your training data set likelihood very different, but the test likelihood might be what is more important for comparing.
Yeah, so you need to do this on the test data, obviously, because we're not completely Bayesian, so the degrees of freedom of the models are not equated, so you need to account for that by cross-validation. Yeah.
Great. That was a nice discussion. Okay. Next question is by Cédric Foucault. Other than brute force cross-validation grid search, are there often used principles for choosing regularization and/or number of features? For example, neurons for decoding stimulus features for encoding. Neurons for decoding or stimulus features for encoding. And specifically in neuroscience, is there examples for that? For example, assumptions of sparse connectivity in the brain or something like that. Sorry, it's a long question.
I'm still parsing. I forgot what the question was.
So essentially, are there
it's fine. So the cross-validation is, again, it's a way of deciding which model is better. So that's after you've made a whole bunch of design decisions about what your model is. The design decisions are where sort of like expert knowledge about neuroscience or domain-specific knowledge comes into play, and that's a little bit of a black art if you're from the outside. Once you have committed to a model and you fit it, and sort of it's a question of just figuring out hyperparameters. At that level, yeah, you at the very, very minimal thing, you can do a sort of a brute force grid search, or you can do something more sophisticated. So actually, the kind of stuff that we do, we typically have some fancy ways of jointly optimizing the parameters and hyperparameters. So you just cast a bigger umbrella, you make everything a big optimization problem, and try to be clever about navigating that space without getting into much trouble. But depending on the details of the model, exactly what you're trying to achieve, how many hyperparameters you have, different kinds of solutions might turn out more practically useful.
Yeah, it really, like, if I can just comment about this, so these aspects of machine learning seem to be a bit of like a dark art that you sort of like have to learn by doing and experimenting a lot and gaining an intuition of what different manipulations do in terms of optimization, in terms of parameter, number of parameters, etc.
Yeah, but even us, that sort of we've been doing this for years. So sort of like if you see a completely new data set you have no experience with, it's going to take you a few iterations of trial and error to get this working on a new data set. It's not like completely, oh, I know how this works. Whatever data you give me, I'm going to sort it out in one go.
Yeah, there is a field in pure machine learning to just try to do hyperparameter optimization to make the hyperparameter search easier. I see meta learning mentioned in the chat, yeah, but also many similar like hyperparameter search network or something proposed to do that. People are interested. You can take a look at that. And also, when you do a lot of Bayesian, as what I've been doing, there are actually some smart way of doing the hyperparameter selection automatically in Bayesian model that you don't need to do the brute force cross-validation yourself. And although you can't really like do gradient descent on some hyperparameters, but you can still try to use some prior to generate these hyperparameter and to fit the model, which is quite magic. Maybe it's too advanced to talk about that here, but people shouldn't be so desperate that you have to always do brute force. But this is irrelevant to neuroscience. This is purely from the modeling perspective. And in the area of neuroscience, I think people could apply some domain knowledge, to add, say, sparse connection to neuroactivity. If you know, like this region won't be very directly related to the other region, or both spatially or functionally, then yeah, you can eliminate that connection a priori if you want. There is way to add to impose some knowledge to the model a priori in neuroscience. But yeah.
Good points. It's interesting that all three of us are very Bayesian. So let me give you a non-Bayesian comment on this.
Thank you.
So cross-validation itself is it's a very powerful tool, but one of the weaknesses is that your data set, you're chopping your data set into smaller pieces. So, and oftentimes in neuroscience experiments, your animals will not do millions of trials. They would do like 100 trials or something like that. So your data set is sometimes very small, and cross-validation, if you chop it into half, or if you do a nested cross-validation, then you're really limiting your own data sets. So in traditional statistics, has some powerful tools here in that realm. I'm not a big fan because I'm Bayesian, but I'm just letting you know that there are these tools. There are tools for penalizing and using your entire data set to fit it, right? So basically what you were trying to do in cross-validation is to not overfit your parameters. So what you want to do is penalize your model for that exact amount. And there's principled way of doing so called AIC and BIC and these information criteria. The AIC is short for Akaike information criteria and so on. And if you're really limited in this regime, then you might want to go look into those settings. And another thing just to mention is all of these approaches, like the cross-validation or the marginal likelihood approach, the more Bayesian approach, and this information criterion type of approach, these may not give these, they might disagree on their optimal parameters, and that's just the fact that they're not supposed to agree anyways. There are no principles to tie these together. They're all different principles, but it's okay.
So can I maybe ask, since you mentioned that, so what do you do in that case? If you want to interpret those parameters in some meaningful way with respect to your neuroscientific question, and different methods essentially give you different answers, and what do you do? How do you interpret that?
Correct. I think we're sort of like we're too inclined to directly interpret parameters of models with respect to actual real data stuff. So just the fact that the model fits reasonably well, like that among all the models that you tried, this particular model fits the best to your data doesn't necessarily mean that it captures the true underlying structure of how the neural responses are being generated. So it could be that you're sort of like you're ignoring some important structure there. So the correct model is not even in the space of things that you've tried. So if you force a wrong model to fit the data as well as it can, it will do something, because by construction it has to do that. But it doesn't mean necessarily that the parameters that it comes up with are going to be extraordinarily meaningful with respect to the real world. So I think there's things that you can do with sort of like whether or not you have like non-zero weights with respect to one particular stimulus dimension. So whether or not the neuron cares about that stimulus dimension at all, that's something that you can ask. Whether this particular shape of the filter is exactly what the neuron cares about, there's sort of like, it's going to get complicated because, yeah. Anyways, so some footnotes and grains of salt are required in the interpretation part.
Right.
I'm not coming up with a good example right now.
If I may add a little bit, I mean, these disagreements are usually more prominent if your models are, if your data is very small or your signal to noise ratio is really bad, right? In that case, you're digging in small things. You're trying to find small signatures of supporting your model from very noisy data. And that's probably why these are good for generating hypotheses that you want to test with experiments in the future or with larger data sets, right?
Yeah.
So, but if they disagree, that's probably a good signal that it means you don't have enough data, or your hypothesis is too weak, or your data is not supporting your model very well.
Yeah. Yes, more often than not, the best solution is to beg your experimental collaborator to give you more data, which is also the hardest thing to do.
Great, thank you so much. Okay, the next question is by Xiaoxiong Lin, asking, what are the best ways to prove or confirm sparsity of data? Very practical question.
Prove is a very strong notion.
I don't know how to prove anything.
Yeah, statistically speaking, we just have more and more confidence on it, but not prove. Sparsity of data. I guess what they're asking is
sparsity of the model, probably.
Might be. If it's just a data question, you're just maybe reiterating the definition of sparsity might help, right? For us, the sparsity is just number of non-zeros, really, the proportion of non-zeros.
Yeah.
So if you have a million data points, but most of them were zeros, that's a very sparse data set. There's no hard threshold.
Yeah, spectrum is sparse.
Depends on what binning.
I mean, the thing is, yeah, the sparsity of the data is very different from sparsity of the model. Like spectrum is sparse, but the model is not necessarily sparse, and vice versa. So I think what he asks is about the sparsity of the model, why we could use L1 penalty to it, and why this L1 penalty makes sense. If the model is not sparse, then if you do L1, you don't really get the good performance. Like usually for me, you can check the performance empirically, right? You have a non-sparse model and sparse model, and you will have different predictive performance on test data, and then you will know, like, okay, then the sparse model makes more sense. I think from us, where we do statistical modeling to it, so we don't have proof to anything. We just, the data tell us what we should trust. That's how I usually work. I mean, if you have theoretical proof, that would be good. But if you don't, then you can only rely on data and rely on what data tell you. Okay. Xiaoxing said that's what he means by sparsity.
You hit the spot here. Perfect. Okay, let's see. We have some more questions here. There's another question by Ken. Whoops, that just got overvoted somehow. Okay, I'll ask a question then by Krasimir. Elon Musk's Neuralink feasibility, safety, potential, question mark. Oh, that's an open question. Okay, so what do you think about Elon Musk's Neuralink? Is that actually feasible? Is it safe? Will we actually ever be able to do that safely? And what's the potential for the future?
I have no opinion that I want to voice in public on a recorded video.
Interesting. I mean, I would ask this question back to Elon Musk's Neuralink. Are they using GLMs? If they are using GLMs, yeah.
So this is a question that you should send an email to Flip Sabis, who is a professor at UCSF and who's the scientist in chief at Neuralink. So he's a electrophysiologist that has worked a lot in motor control, and he would be probably very happy to actually answer those questions. Yeah, so I mean, does anyone want to comment on this?
No.
So I actually want to comment briefly on this because so you can think about the stated goal of Neuralink, whatever you want to think about that, but the fact is that in terms of technology development, this what they call like the sewing machine, right? That inserts the flexible wires at very specific locations of the brain has been like a real feat of technology, and like all like electrophysiologists, researchers hope that this will be publicly available at some point, because that is a real step forward in terms of what you can do technology-wise in terms of recording. So whether ever Neuralink's stated goal will actually be a reality, we will see. Time will tell. But in the meanwhile, I think that's the effort and the funding spent in that research direction has a big potential of really helping the field of neuroscience in the long run. And so to me, this is a positive thing. Despite the fact that it's a private company doing this. But so, all the recording devices that you can buy for your EFIS rig, they're all built by and optimized by companies. So this is in this way no different. Okay, that was a fun question, kind of. Okay, now
people have lots of opinions in the chat that are a lot more informed than ours would be. So feel free to read that.
Well, and this is obviously a question that we can talk about for hours now, and like get into all kinds of philosophical conundrums and things. But I think this might be better over for over a beer than here. Okay, so a question by Karen Netakoven. Are the decoding and encoding functions inverse of each other, or do they bear any relationship at all? Haha.
Good question. Good question.
You can do a decoded by inverting an encoding model. That involves Mr. Bayes again, which we're not supposed to talk about. But they are mathematically related. The way we were using the GLMs, we were sort of like trying to fit directly an encoding model and directly a decoding model for these purposes, so not doing an explicit inversion. Yeah, the explicit inversion involves a prior, and whether or not that prior is easy to estimate, easy to write down, easy to compute with, how do you want to go about it will depend on that.
Great. Thank you very much. Okay. Oh, look, now we're coming to Ken's question. Okay. In today's tutorial, in comparison to the linear Gaussian filter, nonlinear Poisson filter shows higher weights at some time bins in the window. Does that mean the data is highly nonlinear? How can we tell which model interprets the data better when the two models show a similar trend, but only some weights are higher than the others?
Anqi?
So I'm reading the question. Just like a long question. Poisson filter shows higher weights at some time. I don't think one weight is higher than the other means this is a better model, because you might have a very high weight, but which is due to the noise or something. So I usually I don't judge a model, or I don't judge models by how high the weight are. I usually if you somehow, okay, for simulated results, for simulated data, where you know the ground truth, then what you should do is compare the weights instead of saying which is higher, because the higher the weight is, it just means this neuron is more related to the stimulus or related to the behavior. It doesn't mean it's good or not. It's higher correlation or not. So usually when I compare models, show a similar trend. I don't really understand what this trend means, but usually when you compare models, you only compare the predicted performance on model on test data. You don't check the weights, compare two weights and see, oh, which one is better.
Can I add something?
Yeah.
So in the intro, we had this one example where of the poorly fitted filter that had really wiggly weights, that you had really big weight values, but it was just because of you were overfitting the noise. So big weights don't necessarily mean anything. That was sort of like a cartoon counterexample that we had in the intro.
Yeah, I think this is where the question is going.
I mean, typically, if you for the same input-output data, if you fit a Gaussian versus Poisson model, they would look similar, but the real question is which model is better, not, is the weight, when the weight is higher or lower. You can't really say if that's your evidence, right? It's really the predictive power of the model after you fit. Is it better or not? Yeah.
Great. Okay. Oh, another stochastic and deterministic. So that's a question by Margaret Magnus. Two terms that have been used in the tutorials but not defined or explained are stochastic and deterministic. Can you give a definition of these terms in relation to the topics discussed at Neuromatch Academy up to this point?
Okay. So I think August's answer is perfectly fine. So stochastic means that there's a noisy component that you're not controlling for. Deterministic is that you get the same answer over and over again. So typically when you talk about variables, whether or not you treat the variable as a random variable so that there's uncertainty about what the value is, or you actually think it's a single number that you maybe try to estimate or something, but you're not treating it as a probabilistically, but as a point estimate. Oh, and now I'm introducing the term point estimate, which is a single number. It's very hard not to accidentally use stuff that I'm not supposed to.
Yeah, I mean, go ahead, Anqi.
Oh, I just want to say, like in the tutorial, for example, if we get back to the model fitting on day 3, right? At the beginning, we introduced MSE model. Y is theta multiplied x. Everything is deterministic here. There's no noise. So in this case, Y will be deterministic. And when we get to the MLE, where Y is theta multiplied x plus noise, now we have uncontrolled term noise to generate Y. So in that case, Y will be stochastic because of the noise. So you can think of the output in MSE is deterministic, and output from MLE kind of model, not MLE model, but like the noisy model is more stochastic. Yeah.
Memming, did you want to add something to that, or was it the same point?
I could add a little bit. So this whole stochastic portion, in terms of a Bayesian perspective, which is going to come in week 2 for those of you listening, is not necessarily that the nature of the process, like we're not saying the brain is deterministic or random. What we're really saying here is, as far as in the Bayesian interpretation, our knowledge about that system is incomplete. So we don't know something about that system. So that part can be modeled as random in some sense. So in many of the cases when you're fitting these kind of statistical models, being stochastic does not mean that we believe that the target system is random per se. It's just there's some mismatch between the models. There's some unknown knowledge. There's some, issues possibly with the measurement, which would be a real noise, but not necessarily a deterministic system is being modeled. Yeah.
Awesome. Thank you so much. I hope that clarified things. Okay, question by Marcus. Can you give a mathematical justification for why L1 regularization picks out important parameters?
Important.
Yeah, that is very subjective.
I don't know what important is. The only thing that you can show is sort of like in the cartoons that we were trying to show is that it gives you solutions that are typically more along the axis than the L2. So the solutions tend to zero out some components. What important means? It's not like the ones that, because you're trying to fit the data, well, presumably the ones that you keep non-zero are there because of a reason, but yeah.
Here's how I think about it. I mean, there are many different ways of making your model sparse, but what's common to them is that you want the parameters that are strongly supported by the data to survive, and the ones that are weakly supported by the data to be pruned away. If you have to prune away some of the parameters, right? So in L1 regularization, as you crank up the regularizer, you'll be pruning out more and more, and hopefully the ones that are pruned out first are the ones that are less supported by the data. And most of the time, these weights are the small weights, not necessarily, but they're the smaller weights. And what survives are the big weights that are strongly predictive of the output.
Mm-hmm.
Great. So I think we should take one last question before we wrap it up. Here's sort of like a little bit more of an open-ended question, maybe, by Francesco Sacadura. Is there any biological motivation for the assumption that neural encoding and decoding is linear, apart from simplifying the maths?
So the way neurons communicate, there's a hand-wavy argument that you may or may not believe. I will try to explain what that argument is, and you can choose whether or not to believe it. So the way neurons communicate to each other is by synapses that are kind of linear things. So they're linear processing units. So if you think about how an extra neuron outside of this population gets information about the neurons within this population, you can think about that as a first approximation as a linear filter. So that might be a reason why you might think that decoding of information from one population by neurons in another population might be linear. As I said, you don't necessarily have to believe this, but this is the kind of argument that people have in mind. A lot of it is really mathematical convenience, to be honest. But if you want to go beyond that would be one way to think about it.
In terms of decoding, I would say if you have an arbitrarily powerful decoder, like a universal approximator type decoder, you can sometimes decode too much. I think I mentioned this in the outro. And if the goal of your analysis is to understand what the neural signals mean in terms of to the brain itself, not to a super powerful machine learning tool, then you want to know sort of the code. I mean, that's a whole part of the analysis, right? You want to understand what the code is of the brain, and in this case, you want to limit your power of your analysis. And the easiest way of doing so, as Christina was mentioning, is to assume a simple model, such as a linear model. You can go a little bit more complicated. You can use a quadratic model, which people sometimes do, and there are slightly more nonlinear models that are still in the biologically relevant regime. But of course, we don't know exactly what the code is. We don't know exactly how they're being used. But it seems to be a good proxy so far. And so practical terms, it's very useful to do this kind of analysis.
Yeah, it's also sort of a little bit of an Occam's razor kind of thing that you want to understand the simple structure before you go to any more complicated structure. So that, again, first pass of understanding might be a linear model in terms of interpretability as well.
Great. Thank you so much for all these answers. So we're coming up to the hour, so we should slowly wrap up. For those questions that have not been answered, I encourage you all to please post them in the NeuroStars forum so that you will get an answer to those. And then maybe I can invite all of our panelists to say a few brief last words. Any words of advice or wisdom you would like to give to the students in terms of maybe specific to GLMs or in general? How would we go reverse? Anqi, do you want to start with that?
Oh, yeah, sure. So one thing, congratulations to you guys, is you have already moved a step forward from model fitting to more complex model fitting. And then you're closer to like computational neuroscience and to really analyze the real brain data. So, and you will get to know even more complex models in the coming weeks or days or weeks. But for the model fitting part, basically yesterday's tutorial and today's tutorial are like the main workforce people would rely on. So actually, you can start to do some simple neural data encoding or decoding already. If you're an experimentalist, you have some data, and then you can start to do some analysis with GLM. And there are a lot of interesting extensions of GLM. I think Memming has mentioned a couple of them. But still, GLM, the thing we introduced in the tutorial is very basic, and I would encourage people to learn more about all various kind of GLM by searching the literature, which are really interesting and helpful to analyze the real brain data. Yeah, I won't talk too much about this, but yeah, I think GLM to me is a very, very powerful tool, and hopefully by the end of day 4, like knowing the knowledge from day 3 and day 4, now you have a more systematic way of thinking about how to do modeling and how would I fit a model to my data given different property of the data, like which noise I have and which kind of nonlinear function I should use. Yeah, hope you guys learn something from these 2 days model fitting tutorial.
Thank you.
Yeah.
Christina.
Yes, I want to echo Anqi's comments. So I think that although it seems like a lot for digesting in a day or 2, these are really fundamental things, and they're really powerful and really used a lot. So if you understand these things, you're actually making a really big step ahead in terms of actually being able to do a little bit of actual neuroscience. So in terms of data analysis modeling, there's a lot of other sides of computational neuroscience that we're going to learn about later. But in terms of data modeling, this is actually a concentrated, minimal things you need to know in order to start getting stuff done. And everything more complicated is sort of pretty strongly relying on this conceptual basis. So if you get this well, you can go far. Memming.
Yeah. Well, final words. I think Conrad mentioned, if you like GLMs, consider advanced machine learning techniques, promoting work from his group. I would say sometimes when you look at machine learning, which is advancing in super fast, in so many different directions, there are many different fancy things that are very flashy and very attractive. But if I had any wisdom to offer, is don't chase all fancy things simultaneously, and make sure that you have solid basis before you go for fancy things. And in solid basis, I would say GLM is one of the most fundamental things you should try. But of course, more importantly, you should have fun doing science.
I like that as an ending.
Thank you so much, everyone. That was great. I'll see actually all again in a few hours, and then tonight, I guess, in the Americas time zone for the Americas Q&A. Thank you so much for joining us, and see you later.
Bye.